Hello, you're watching Science of the World. Now today I want to talk about something that I find very interesting, and that is electricity. It's somewhat mysterious and something that you can't see, but it's there. And it's something that holds our life together basically every day, every single day. And without it, this world would be a very different place, and people wouldn't be able to cope in some cases. So this mysterious force I'm going to talk to you about. I'm going to talk to you about the bare electricity, like lightning, and how lightning works, because that is also a form of electricity. Electromagnets that are electricity. Fuses, how fuses work. Amps, volts, and all the different types of circuits. And also what the future might be like without electricity in the future. So to start off with, I want to talk about lightning. Now, lightning is something that is very bare, and something that is not in our control. We cannot control lightning. We can control electricity, but we can't control lightning. Now, this is the bare form of electricity that is in its first stages and is very dangerous. And you can't mess with lightning. It basically has killed lots of people in some extents, and it's also caused havoc with some lightning storms, some of the worst lightning storms being in tropical places. But so how does this strange force work? Well, basically, when you get a thunderstorm, lots of things happen. One of the things that will happen first is rain. Now, rain will happen a lot in thunderstorms. Basically, what happens in the clouds, you have some clouds which will be negatively charged and some which will be positively charged. And basically, these two negative and positive will rub together, creating almost like an explosion. This explosion will create this small electric charge. Now this will happen on a massive scale. All the clouds will be almost rubbing together, and also the raindrops will be rubbing together to create this small charge. Now this charge then slowly turns into an explosion, and this massive explosion then turns into lightning. It's a massive form of electricity. There's about 4,000 volts in a lightning strike. Now the lightning strike will strike the earth. But more specifically, it will always strike the earth. That something, because the earth is almost like a giant magnet, it has lots of iron and metals in there, and it's almost like a big floating magnet in space almost. And because electricity is attracted from a magnetic field, it will always strike a tree or something that is standing straight up that goes into the ground. This is because the lightning can graft onto something which is closest to the ground, and it is easier for them. For example, a tree puts its roots into the ground, and in the ground and in the soil there is hints of magnesium, iron, and various other metals. But also, even deeper than that, there's lots of metals. So it's basically easier for the lightning to come onto something. So it's attracted to something that has a magnetic field on it. For example, a tree, or in some cases, if a person's standing, a person. But it's very unlikely to be struck. You're very unlikely to be struck by lightning, although some people have. Now, this can cause dramatic consequences. 4,000 volts for you, you ain't gonna survive, 100%. But you see, the thing is that lightning, we can't control it. We will never be able to control lightning. Maybe we can harvest it in some way. I know that's a bit of a strange word to say, but it's pretty much out of our control for now. And it's very powerful. It can strike trees because it's magnetic, and sometimes us because we are standing on the ground and we're taking in some of that magnetic activity. We have iron in us. We have metals in us. This is why it's so important not to do this. Now, something that I want to explain very quickly is basically what a Faraday cage. Now, a Faraday cage was invented by someone called I forget his name now, but he was the guy who basically discovered lightning and how lightning worked. Now, he invented this thing called the Faraday cage, which is basically a human cage which you can stand in, and if lightning hit you, you would be absolutely fine. 4,000 volts can protect you from that. And all it is just a metal mesh, like chicken wire. And that's all that it is. It's simply that he found out that actually metal, even though that lightning is attracted to it, that's what will happen. It's more attracted to the metal. But also, another thing is, this type of metal, there's two types of metals in this Faraday cage. One that is positively charged and one that is negatively charged. This can be any types of metal. Basically, what happens is there are two on both sides. So if you imagine if this is the Faraday cage, negative, positive. Now the negative ions come together to create a discharge. Now this discharge is something that made lightning first of all, but actually can also protect you from lightning itself. This discharge can actually run around the cage, protecting you. Now what happens with a charge, so the positive ions from the lightning come on to the negative ones, and they're protected. They create a discharge, making it fine. Discharge is absolutely fine for a human being to survive. That's why if you're in your car and lightning hits you, you're absolutely fine. It will blow out your tyres, of course, because lightning can penetrate things like rubber, but you'll be absolutely fine because you were in that metal almost box in a circumstance. So cars are also like a natural Faraday cage, and because of that experiment, that Faraday's experiment on, we can now furthermore it on into more scientific research. Now that was all about lightning, but something I want to explain now is a fuse. Now, I'm going to explain a fuse now. Now, a fuse is something that we use in everyday life. A fuse is in all electronical items, and they have a very important job, and basically stop household products from basically exploding. Now, this is what a normal fuse usually looks like. If I get my pen here now, this is not very good drawing, obviously very rough. A fuse is something like this. It's just very, very small, no bigger than this. This is obviously not to scale, but it's basically a very, very small cylinder. Now this small cylinder actually contains a small thin strip of wire running through it and then running out. Obviously you can't see this because it's all shaded in, so you can't see it. But actually, this very small string of wire is actually very thick. Now if I draw it out here more to scale, imagine if this piece is the wire. Now it contains lots of different wires. So if I get this green one here, so imagine that this green strip is magnesium or iron, and then this orange one is another metal. Now this is what basically a fuse wire contains. Lots of different alloys and lots of different metals. And all these metals come together to protect the product from exploding. Now, as I said before, they are in all electrical plugs and products. For example, they're in TVs to stop them from exploding, hoovers, anything like that. And all electrical products need the fuse. But in fact, what even is a fuse? Well, basically, a fuse is something that protects the product from exploding. Now, I'm going to say something called electrons. Now, electrons, I suppose you could say, are kind of little electricity particles. Now, these particles run around in a stage. So imagine if I draw a circle. That was not a very good circle, but imagine if that is just, a good circle. And basically what happens is all the little electrons flow around inside the metal. So you have all the little particles running around through the metal. These electrons here all flow around and around and around and around. And basically they're things that carry electricity. That's all electrons are. They just carry electricity. They're like small atoms, particles of electric. And they basically just run around helping a product to work. So a television has wires in it. And in those copper wires, because copper's the best way of installing electricity, they'd be running around almost helping, as you were, the particle stages. Now this is very, very easy for them, but basically what the fuse does, if we go back to our badly drawn fuse, is basically it kills any excess electrons. And that does seem a bit weird, because surely once that has happened, the product won't work. But if you can imagine, if there are too many electrons coming through, if it's supposed to be one after the other like this, and it happens to turn into this, the fuse will kick in and kill basically destroy with a discharge any rogue electrons. Now, if these rogue electrons got through to the electric product, then that could lead to a very dangerous situation. The product will explode, it could possibly cause a fire, and that could create big danger. So this is what a fuse does. A fuse has a very important job. Now, back to go into the metals, it has lots of metals in it, because these metals can all work together and they can make a thicker wire. Now, the wire in the fuse needs to be as thick as possible, because it's trying to kill all of the little electrons. So it has to be bigger than the electron itself. And that's basically how a fuse works. Now, there are lots of different types of fuse. Now, fuse are measured in amps. A for amps. And that's all they're measured in. Amps. And you can get things such as a 3 amp fuse. You can get a 5A fuse. You can get 7, 10, and top one is 13. And some electric products maybe even more than that. But the basic household products are just that. And these products obviously are very helpful. And it depends on what product you have that the amps kill. Because if you put the wrong fuse in, too much of that fuse is too many electrons are going to be killed. And again, you're going to get a bad fire explosion. But still, it keeps going. And I mean, for example, let's say a radio. If we have a radio, radios tend to have 5 amp fuse, because 5 amp fuses are quite small, and a radio doesn't really need as much power. So that's why it has a 5 amp fuse. For example, if you had a washing machine, a tumble dryer, or an iron, they're using lots and lots of power, so they will need a 13 amp fuse. Now, that's how it works. Depending on how much power it needs, there's a different fuse setting. Here I have a opened plug. Now, always be careful when you open plugs like this. You can do it, but you just have to be very careful. And here we have an open plug here, which has an opened up fuse. Now, I don't know if you can see this because the light is quite poor, but if you look very closely, this actually is a 13 amp fuse, and as you can see, the fuse runs here. It says 13 amps on it, and here are the two. So the fuse obviously needs power, and inside this fuse will be a thick bit of wire, which is killing the electrons that run through the wires here. Now, next product that I want to go on is the wires. Now, here we have lots of different wires, and now this one I'm going to pull out here on the third wire of the plug. This is obviously the point here, like that. It's obviously a long metal bar for the disc. It might have a bit of gold in there as well in some cases. But what we're interested in is the wire that connects to it. Now, this wire here is called sometimes it has lots of names. It has the earth wire, live wire, various things like that. And now it's coloured as green and yellow. And actually in future it was actually brown. But that colour has changed because, would you believe it, people with, seeing abilities and colour blindness are actually more able to see the colours of green and yellow together rather than normal colours on their own. So people who obviously are electricians, it's much easier for them to see. That has happened over the future, and in the 1980s it used to be brown, but now it's this colour of the green and yellow. There's the other two wires. If I just go to the end here, we have the live wire, which I said before is there. We have the brown wire and the blue wire here, and they all connect to all the different pieces of the material. As you can see, they all connect to the 3 plugs, this plug that I've just pulled out now. But they, it's all very simple to put back in. So that's basically how the plug works. This is what's inside of the plug. Now, as I said before, you can take away these plugs to see what was in them, and it's very, very interesting. But always be careful when holding electricity. Now, it's very interesting to see why some countries have the 3 plugs like we do, and some others have only 2. Now, this is something that I've tried to find out, but I reckon that it's always to do with the magnetic field in some cases, but it's also to do with how powerful, I suppose, the products work into countries and various things like that. So that's basically how the plug works. Now, quickly moving on to circuits. Now, there are lots of different types of circuits. There are 2 types of circuits. 1, which is parallel, and 2, which is series. So series and parallel circuits. Now, they are very different and actually require different things. So, for example, I'm going to draw a simple circuit out now. So this is the wire. This is how you draw a symbolized circuit, which is basically drawing a symbol circuit just using symbols. Now, this circle with an X in it represents a bulb. Now, so this is a bulb. This one here represents a battery. If I just turn it up round the other way, represents a plus or minus. Now, a battery sometimes is very complicated. Actually, a battery is sometimes drawn like this, plus and minus, because it's a lot more complicated. But this here is what we call in science a cell. Now, a cell basically just means a source of power. That's all it means. If you don't want to draw the battery, which is something a bit different, you can just draw the cell symbol. So that is basically a very, very simple circuit. Now, this is basically a series circuit, which is probably one of the most simple things ever. Now, I might have got that wrong. It might be the other way around. But it's probably quite a simple circuit and is used in pretty simple things. This is a very simple circuit, and actually not many people use it. So, for example, if the power source was cut out, then so would the bulb. Because there'll be no more electrons coming from the power supply. And so basically, everything will die out. So basically, this is not used in many products because it's be awful. So for example, the series circuits in your house. Imagine if your power went, all the lights would go off. And that's what usually happens. That's basically what most houses use, because when you have a power cut, all the lights go off. So in your house, it'd be a series circuit, but in some cases, it's a parallel circuit. And a parallel circuit usually has backup power of supply. So basically, it will be more complicated. So it would have 2 butts here, with 2 bulbs instead of 1. Now, it will be joined up in something like this. With, instead, there be 2 power supplies in some cases. Now, this is called a parallel circuit because 2 wires cut into it. So if one power supply cuts off, then the other can kick in. This one might go out, but usually this one would stay on. Now, if I've got that right, this is what sometimes a parallel circuit will look like. Because there's 2 lines here in parallel line that don't meet. So basically, that's what a parallel circuit will look like. Now, they're used in various things like products which will need a backup power supply when things eventually die and need to keep running. Serious things like hospital machines and various things like that. That was my presentation on electricity. And as you see, I've been talking for about 20 minutes now. It's something that I find very interesting. But now we're going to try a little science experiment, or sometimes it could be a magic trick as well. So stay tuned for that. So for this scientific explanation slash magic test, you're going to need some scissors, some matches, some sellotape, some food colouring. This is red. You can have any flavour, any colour you want. A 2p coin, some water, and a plate. So basically, and a friend. You'll need an extra mate for this. And basically, what you're going to do is you're just going to fill the plate with water. And actually, put the 2p coin at the side, like that first. And then pour the water in. Pour the water in so the coin is just submerged in the water. Get a good amount in, so you can just see the coin is just submerged into it. You might have to add a little bit more to add a bigger effect. Once you've poured all the water into the plate, then oh, and another thing is you will need a mug. As I said, you always need a glass as well. So what you're going to do is you're going to tell your friend, you're going to say you can use these matches, the scissors, the anything you can see here, but you're going to tell them that they have to get the coin out of the water, but their finger is not allowed to touch the water. The matches are not allowed to touch the water. Neither the scissors, the glass. The glass is not allowed to touch the coin, but it can touch the water. But you can also say about the red food colouring. Now, friends will pretty be baffled, but here's the trick. What you'll do is I'm just going to put the red food colouring into the water to make it more obvious to you. So just place some of the food colouring into the water. Give it a good stir so it gets mixed around. So this is basically all it is it's easier to see the trick. So you can still see the coin in that centre of the picture. What you are going to do is you're going to get 3 matches out of your matchbox. So 3 matches here. And you're basically going to sellotape them together. Like so. So make a double-sided strip and then try to stick the 3 lollies into the coiled mixture. Obviously this is going to be very hard because it's wet. But, so, you should be standing up like that. Then what you're going to do is, okay, so with your matches in the water, you're now going to have to light it. Okay, so this is going to have to be very quickly. You're going to have to light it. So light the matches, and then quickly put the glass on top. Now this might not work, but hopefully all the water should actually get sucked in to the glass. So let's see. So there you go, guys. All the water has got sucked in, and now you can simply just take away the penny. And then you can say, there you go, I've taken away the penny without touching the water and without any of the other items doing it as well. So that is how you can amaze your mates. Now, I'll quickly explain the science here. Basically, what's happened is the matches have created a small vacuum within the pieces. Basically, it's a small, very hard vacuum, and they've created a small vacuum. Yeah, I'm just seeing if I can move this, but you might have to leave it for a while. They created a small vacuum, and the water's been sucked up. That's basically what's happened. So please subscribe, guys, to my videos. Watch all my other videos. Just type in Science of the World on channels, browse channels, and that's all to say, guys. Thank you for watching.